Hey guys, this is lesson 2.1. We're starting into our next unit, which is quadratic functions. And right now we're just looking at the parent function and the introduction. So in order for us to do this, you're going to need to set up your paper in a Frayer model. A Frayer model is just a way to organize some ideas around like a new vocabulary word or like a new big topic. So make sure to turn your paper horizontally and draw out the sections for your paper. So that means that your 3-hole punches should end up either at the top or at the bottom, either way, one or the other, not both. And then make sure you use your whole paper as much as possible. And then go ahead and fill in the labels before we get started with notes. All right, let's start in the first section. So our first section is the parent function equation. So first off, let's just make sure that we understand what a parent function is. So a parent function is pretty much a fancy word or phrase for when we're talking about the preimage or original. So what we have been doing is we've been transforming shapes, like two-dimensional shapes. But what we're going to start transforming and building is functions or graphs of like different types of lines. And so our parent function is our original, aka our preimage. So let's try to understand what we mean by like a function. So we've been learning over the course of middle school and Math 1, different like patterns to functions. So one of the patterns that we learn is a linear function. We talked about that a lot more last year in Math 1. A linear function means that the largest exponent here is a 1. We don't normally write it because it's invisible. The next level is quadratic, which is normally we have an x squared. So again, you need to have an x squared. Then it keeps on going. Just to kind of lead you on, we have a cubic, that would be x to the third, and we have other functions too that, again, just depending upon what the exponents or maybe some absolute value bars or things like that. And again, the unit that we're starting off is specifically focused on quadratic functions. Now, quadratic functions are also called second degree functions because, again, that largest exponent of the variable is a 2. Now, we're going to be looking at how to transform this function, but the original, the pre, that is just y is equal to x squared. All right, let's look at the graph of a parent function. So again, I would pause the video and sketch some of this out. Make sure that, again, you're doing the best that you can for graphing. I know it's not perfect. So when we go to graph a quadratic parent function, we call that graph a parabola. And to definitely throw it back, let's look at our x and y chart. So let's come up with an x value. So remember, our x value goes from left to right. So I want to start with some negative numbers and move my way from left to right across my graph. So that way I have a good representation of points. So let's do like negative 2. So if I'm using my equation of a parent function, that means I would have negative 2 squared. Because again, I had my x, that was my input there. Make sure we put parentheses because we have to make sure we're squaring this correctly. So that would mean negative 2 times negative 2. A negative times a negative is a positive. So my answer is 4. So this is my first coordinate point. I need to go to negative 2, 1, 2, and then up 4. So again, approximation, it should end up right there. All right, let's look at negative 1. Okay, negative 1 squared would be negative 1 times negative 1. A negative times a negative is a positive, so positive 1. So my next point is going to be at negative 1, positive 1. And again, just a little sketch. That point would go approximately right there. All right, let's do 0. All right, 0 squared, 0 times 0, which is still just, 0. So notice we start seeing this shape. Okay. Well, let's go ahead and do 1. That would mean I need 1 squared, which is 1 times 1, which is still just 1. All right, what about now 2? That's going to be 4. Interesting. I see some symmetry here. Because again, this looks like almost a reflection. Just for funsies, let's do 3. Oh, that jumped up really high. So let's see if that even fits my graph. So 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8. If I make another spot up on the very top, we can make this fit kind of approximately up here, 9. So when I'm betting you there would be a point on the other side, I'm betting you it would be at -3 and then up to 9. Because again, we've got some symmetry going on. Now, when you connect these dots, please make sure that you know that the shape is always a U-shaped. So make sure we have a curve here at the bottom. I would maybe start with that curve and then connect the dots going up. And then we should have an arrows at the top because technically my graph keeps going. So this is what the pattern of a quadratic function looks like. So some characteristics that we need to keep in mind. We need to understand, again, that my shape will always look like a U. Now, we're going to talk about in the future that shape, that U shape could be opening up or opening down. But for the parent function is always opened up. It always looks like a U. We're going to be learning 3 different ways to write the equation. Something called general form or standard form. Something called vertex form, intercept form. We're going to learn how to solve for a couple key points that are on our graph without the graph, and of course with the graph. We can be able to identify but also solve for them. And then we need to be able to describe and compare the function. And of course there'll be more details here and there. That's the main idea. And last but not least, we need some real world application. So why are we learning this? Well, we're learning this because whether you realize it or not, there are tons of things that have quadratic patterns to them. So for example, if you go to play basketball and want to, shoot a basketball into the hoop. So when you shoot a basketball into a hoop, that pattern is a quadratic pattern. You would have a little person here, hi person, and if they go, don't mess up or don't come for me for my little sketch here. So if they are going to go make this basket, it would need to come up and come back down to go through the hoop. And so notice we've got that U shaped happening. Another thing is that's a really important real world one is bridges. So if you can imagine bridges for cars, normally you have some sort of structures underneath. A lot of times those structures are U-shaped. Sometimes even above, on the actual bridge above the cars, sometimes you'll have U-shaped tension wires and whatnot. But for sure, the structure of a bridge is going to have some sort of U involved underneath it. We can even look at just patterns within business marketing. So I always think of a car and the price of a car, because a car starts off being super expensive, but then the price of a car comes down once it gets to be older. But once a car gets super old, like an antique, that price starts to come back up. So if I think about the price of a car, many times that is also a quadratic function. But yeah, there's lots of world applications. Those are just a couple of them that I can think of off the top of my head. But we definitely see quadratics a ton out in the real world, whether you realize it or not. All right. Hope you have a great day.